This board, for example, is a range of plus or minus 600 amps.
Okay.
Single voltage output pin,
Okay.
supply, and one flip pin for flipping.
Hey, it's Eamon with IP Exchange. This is the second of 3 interviews we did with analog devices at Sensor Plus Test. This is a little bit different because IP Exchange is all about very disruptive technology from companies you may have never heard of. And you might be living under a rock if you haven't heard of analog devices. When we went onto their stand, we did see some stuff that was pretty out there. This one probably isn't compared to the first and the third interview, but we still thought it was worth covering, and you know I love magnetics. So enjoy this second interview with analog devices at Sensor Plus Test. Hey, it's Eamon with IP Exchange. We're still at the analog devices booth. I'm here with Luke, and we're here to talk about their contactless current sensing. Luke, can you show me what's going on over here?
Yeah, of course, no problem. So what we have here is ADI's ADAF 1080 contactless current sensor. So it works essentially on the principle of Ampere's law, that you can measure current by measuring the magnetic field generated by that current at a fixed distance.
Nice.
So the sensor itself, it's a bipolar measurement, so we can measure fields in the range of plus and minus 8 milliteslas.
Okay.
And by configuring the distance of the sensor to the conductor, we can adjust the range of currents that we can measure. So here on the board in front of me, I just have an example of the same sensor used in a variety of applications.
Okay.
So these PCBs on the right here, they have the same PCB layout. And this top one here, we have 2 sensors in a differential configuration, which allows us to deal with things like the Earth's magnetic field. We can take a measurement in one direction and the other, average the output, and deal with those stray fields.
Excellent.
So we have a few amps running through the trace.
Okay.
On this same board here, we have an example of a bus bar measurement, the same differential layout, and this allows us to go up to currents of about plus or minus 100 amps or so.
Oh, so this will do the whole gambit.
So this will do the whole gambit. And taking it a step further, here we have 2 varieties of a ring array of sensors. Now, the interesting thing about the ring array is, number one, it allows us to go up to hundreds of amps. So this board, for example, is a range of plus or minus 600 amps.
Okay.
Single voltage output pin, supply, and one flip pin for flipping, which I'll cover in a minute. So the multiple sensors gives us resilience versus wire placement uncertainty, which is useful in a current clamp meter, for example, where the jaw will close around the design. You don't necessarily know where the wire is within the jaw, and in other systems that can lead to error. But by averaging the output of all the sensors, you can reduce error significantly. So over a 500 amp range, plus or minus here, over temperature with some linearity compensation, we have around 1% error over the full range.
Good, very good. In terms of applications, where do you reckon this is probably the sweet spot?
So we've seen a lot of interest from the current clamp meter and instrumentation market, for sure. So where precision is needed, and looking at some of the features of the ADF 1080, you'll see why it's well suited to that. So, for example, here we have noise at 6 nanoteslas per root hertz, and with a range of 8 millitesla, that gives us about 6 decades of dynamic range, or about 100 decibels. So quite high dynamic range. So you can measure a couple of amps with a range, and up to 100 amps in exactly the same, up to hundreds of amps even in the same configuration. One of the other interesting things is we have what we call the flip coil.
Yes.
Now, for an AMR sensor, you can actually bias the sensor one way or another, and that will invert the output. So just to quickly run through it, the output is V set over 2, so you can set it to 5 volts, 3.3, 1.8 to work with various systems. And your zero field output will be half that voltage, so 2.5, 1.65, and so on. So for an increasing field, typically we see an increase in voltage. But if you activate this flip coil, you see a decrease in voltage for an increasing field. The interesting thing about that is it allows you to calculate offset and fully remove it in the digital domain. If you take a measurement positive, you take a measurement negative, you can calculate what your offset is and fully remove it.
Cool.
So no offset in the system, offset drift over life, offset drift over temperature, no longer an issue if you use the ADAF 1080 sensor.
Excellent. So you're just Yeah, that's really good. That's really good.
Yeah, so you can see why that's attractive.
Any magnetic field sense measurement is kind of horrible because we're one surrounded by them and two you've got the Earth's one.
So dealing with those stray fields, dealing with offset, that's where the 8F1080 can really shine.
So what's going on on this graph?
So this is just showing. I have two here overlaid. It's the output from these two PCBs. So this is a piece of user software that we would supply with our eval boards. Nice. It's a plug and play, so you would just connect one of the ADI SDP microcontroller boards, which can, with a bit of a GUI, allows you to tap into the ADC on this PCB and read back. So there's a supply under the hood here that's essentially running through a few DC steps, a few AC low frequency, just to showcase the signal. And to give you an idea of that flip sensor we talked about, if I flip the sensor, you see my reading goes from positive to negative. Yeah. So that's where we can, it's just a small showcase of that flipping functionality.
Nice.
And so what we're looking at is the GUI for the trace measurement, but we can see exactly the same thing on the bus bar measurement.
Cool.
Now, because the distance is increased, we're a little closer to the noise floor, so it's slightly noisier measurement, but the same current reading for both of these boards, whether it's on a trace or a bus bar.
Cool, excellent. And is this the evaluation board that if a design engineer was looking to test this technology?
So this one is available on a request basis at the moment. These two boards, a single sensor board and this ring board, two variations are available of this one with 3 sensors and one with 6 sensors. And more sensors essentially gives you more rejection of stray fields and a higher degree of robustness versus wire uncertainty placement. In a perfect system, 2 sensors is enough, but there's no such thing as a perfect system. Yeah.
Yes. And just to clarify, are those ones available at the moment?
So they're available. Cool. There's stock available on the main distributors for those, and you can find the data sheet, user guides, supporting documentation on analog.com.
Excellent. Cool. Well, that's super fun.
Yeah.
So thank you, Luke.
No problem.
I've already asked your colleague Ben, but how are you finding Sensor and Test this year?
So very enjoyable. It's my first time at Sensor and Test.
Same for us.
Yeah. And so yesterday was a busy day. Hopefully today I'll have a chance to walk around, see what else is on offer. But and while I have you, I might just show you also. We have one more sensor here.
Yeah, I like Joe's Bizarre Adventure. We haven't done the full technical write-up because it's part of the expedited PCIM coverage / Sensor and Test coverage that we're doing on IP Exchange. But you can still apply to evaluate the technology by following the link in the post to the IP Exchange website. Keep designing.